Welcome back to statistics. Now that we've talked about sampling from a population and how to get representative samples by using random sampling, we'd like to think about how to understand the data that we've obtained. There are two main methods that we'll use to do this. One is graphical and the other is more numerical. In this video, I'd like to talk about some graphical ways to understand numerical data. And so as usual, I'll have a few slides and then we'll take a look at the ebook. So let's get started. So when we're talking about graphically understanding numerical data, two of the main tools that we're going to use are histograms and dot plots. When we look at these kind of plots, we're trying to understand what we call the distribution of the data. So what do we mean by the distribution? The distribution of a variable in either a population or a sample gives us information on two things. First, the possible values that the variable takes on, and secondly, the frequency with which the variable takes on these possible values. So histograms and dot plots give us a graphical representation of the distribution of a variable. Here's an example. This is a histogram. A histogram is a graphical representation of the distribution of a continuous numerical variable. In this case, we're looking at the height of U.S. residents aged 20 to 29 years of age, and we're looking at data from a sample of 400 individuals. What you can see here is a bar chart that basically gives that information we talked about in thinking about a distribution. Look at the x-axis first. Over here at the right, it's kind of small, but you see that the x-axis represents height in inches. And you see the possible values running from, it looks like about 59 all the way up to 76. So that's one part of the distribution, right? The possible values the variable takes on. For this sample, heights range from 59 to 76 inches. The bars in a histogram give us the other piece of information in the distribution. That is the frequency with which the variable takes on these values. The higher the bar, the higher the frequency. In fact, you can read off the exact frequencies of the values by just carefully kind of reading the chart. So for instance, heights between, it looks like 62 and 63 inches occur in this data set with a frequency, it looks like somewhere between maybe 33 or so. In fact, I've gone ahead and labeled the bars in this histogram with those frequencies. And so for each range of values here, but you can see the number of observations, the number of individuals in the sample who had heights in that range. So 2 individuals had heights between 59 and 60 inches. 5 individuals had heights between 60 and 61, and so on. So this is a graphical representation of the distribution of the variable height in this sample of 400 individuals. The actual data itself, of course, is a much larger collection of information to look at. Here, I'm just showing you the first 10 individuals in this data set. So individual 1 had a height of 70.1645 inches. You can see the height is measured very accurately here. And we're also recording the gender of each individual. So this is a bivariate data set. The way that you make a histogram from the raw data is you have to bin the data. So you can see here I'm binning the data into classes The first class goes from 59 to 60 inches. The second class goes from 60 to 61 inches. The third class goes from 61 to 62, and so on. And you make what's called a frequency table for the data. That is, for each class, you simply count the number of individuals in the original data set that fall into that class. So that would involve going back and, parsing through your data and counting the number of individuals whose heights fall into each of these classes. For a sample of size 400, you can already see that could be a tedious task. And of course, we're going to use software to do this for us most of the time. But I think it's pretty easy to see how you'd make a histogram by hand if you had to. One thing that's important in making a histogram and the frequency table that underlies it is that the idea of the class width. How far, how wide is each class? Here I've chosen a class width of 1, so that means that there's an increment of 1 in each class. We go from 59 to 60, and then 60 to 61, and so on. And that's what gives us that histogram. But you could choose a different class width. And let me just show you what this same data set would look like if we built a histogram with a class width of 1/2. So there you see that. Now the bars would go from 59 to 59 and a half, 59 and a half to 60, 60 to 60 and a half, 60 and a half to 61, and so on. It's the exact same data, but the histogram looks a little bit different because we've used a different class width. What we want to focus on, though, are the characteristics of the histogram that are really independent of class width. The distribution itself, doesn't depend on the class width. The class width is just necessary in order to get a histogram in the first place. So we want to talk about, when we're talking about, for instance, the shape of a distribution, we want to describe its shape in a way that's not super dependent on things like class width. Here, if you think about the shape of this distribution, one of the things that pops out is that it's got two major peaks. One here located around 64 inches and another located around 70 inches. If we draw a curve that sort of envelopes the histogram, that gives us sort of a more stable indication of what the shape of the histogram really is. So here you see a curve that sort of captures that overall shape. We're going to call this shape a bimodal kind of shape, and it appears, it's the same no matter what class width you have. We want to focus on that overall pattern, not the fine details of how the bars, for instance, here might jump up and down, but the overall pattern is of a bimodal distribution. Bi meaning two, and mode meaning peak. So, mode is a peak, and what we're saying is this distribution has two major peaks. That's what bimodal means. There are various kinds of shapes we're going to be interested in, and let me just kind of go through a few with some examples. This would be a unimodal distribution. There's only one major peak. This is a sample of almost 3,000 individuals, and we looked at the variable body mass index. And so this would be a unimodal distribution. We also would say that this distribution is right skewed, and that refers to this sort of asymmetry in the distribution you see here. It has a long right tail, and that's what we mean when we say the distribution is right skewed. It has a tail going off to the right. So this is a unimodal right skewed distribution. Here's another distribution. This is blood calcium levels in millimoles per liter. The sample is smaller here, just 176 individuals from the United States went into this data set. And we would call this distribution roughly symmetric and unimodal. Um, when I say symmetric in a statistical sense, I'm not looking for mathematical perfection, but rather just sort of the rough overall view of the data set. And so, even though this guy isn't perfectly symmetric, he would qualify as a roughly symmetric unimodal distribution in statistics. And so, the text takes us through several kind of types of distributions, and we're summarizing them here with these curves, these sort of smoothed curves. We're going to call these density curves going forward. But you know, a symmetric unimodal distribution would be something like A here. Here's a bimodal distribution. It's not quite symmetric. Here's a multimodal distribution. You can see at least two and maybe even three or four peaks in this distribution. So one way we categorize distributions is by how many modes they have, how many peaks they have. Unimodal being one, bimodal being two, three or more peaks would be multimodal. Another way we classify distributions is to their symmetry. So here's three examples of symmetric density curves. Yet another way we classify them is with regard to their skew. So here's a density curve representing a right skewed distribution. This would be a left skewed distribution on the right here, distribution B, because the tail goes off to the left. So skewness, either right skewed or left skewed, is something we want to notice in distributions as well. We're going to pay special attention to this particular kind of shape of a distribution. This sort of bell shape in a distribution is often referred to as a normal shape. That's not necessarily because distributions are abnormal if they don't have that shape. Rather, this adjective normal is used to talk about the particular mathematical form of a distribution like this. And we'll have more to say about this later when we talk in detail about normal distributions. Finally, there's the idea of a uniform distribution, which would correspond to a histogram that was roughly even in terms of the heights of the bars here. Of course, when I draw a density curve like that, it's perfectly even. A distribution doesn't have to be perfectly even. A histogram doesn't have to be perfectly even in order to be roughly uniform. But, you know, in the extreme case, you would have this sort of just flat distribution, and that's called a uniform distribution. Again, we'll have more to say about that. So these kinds of distributions, histograms here, describe the distribution of continuous numeric data. What about discrete numeric data? Well, there's a second kind of plot that we often use there, and it's called a dot plot. Let me give you an example here. This is a sample of 410 individuals, and what we're recording is their age in years. And notice the data is all given as whole numbers, so we don't say that somebody's 31.34 years old, although you could say that. The data is given as discrete whole number values. And again, we're recording another piece of data here in this particular data set, whether the person has made a real estate purchase up to that point in their lives. And so that's a categorical variable. And again, we have a bivariate data set. But right now, I'm just going to focus on the age variable. How could we plot the distribution of age in this data set? Well, we can use what's called a dot plot. Since all the data is in whole numbers here, we can just represent each individual with a dot and put a dot in the plot every time an individual has that age. And then if individuals have the same age, we just stack the dots on top of each other. So from the dot plot, you can immediately see that in this particular data set, there were two individuals who were 19 years old, one individual who was 20, two who were 21, and then one, two, three, four, five, six, it looks like seven individuals who are 22, and so on. So this is a dot plot for discrete numerical data. But again, you can kind of assess the basic shape of the distribution very much in the same way as you would for a histogram. This would be a unimodal distribution, roughly symmetric, although you might detect a slight left skew to this distribution, and so we could describe its shape that way. Okay, so that's a brief introduction to some of the types of plots we use for numerical data and how we describe those distributions in terms of their shape. Let's take a look at the ebook and see what it has to say about this topic. So we're actually going to skip a little bit. We're all the way down here in Module 6 now. So let me pop that open. And the section we're looking at is 6.1a. So let's see what that has to say here. Again, the key concepts are given in the first section of the chapter. There you see those distribution types I talked about before. And then they'll run through an example or two. Here is an example given in terms of a dot plot of the number of math problems that some school children were able to complete in 1 minute. So you would describe the shape of this distribution as roughly symmetric and unimodal. And there you see a density curve that roughly approximates that shape. Here's another distribution. These are values returned by a random number generator. We'll be using random number generators as we go forward to pick samples and do other things. You would describe this distribution as roughly uniform, right? Because although the bars aren't exactly of the same height, they're roughly of the same height. And so this would be a roughly uniform distribution. Let me just pop open a couple of other of the examples in this section and let's take a look at them. Let's see. I wanted to look at homes for sale. Here's a distribution of the selling prices of homes in a neighborhood in a small rural town. How would you describe the shape of this distribution? Well, let's take a look. First of all, notice the units here are in thousands. So home prices in this sample ranged from, it looks like a minimum of around $20,000 up to a maximum of $240,000. And this would be a unimodal right-skewed distribution. The selling prices of homes here are concentrated, it looks like, in the area from maybe 60,000 to 100,000, but you do have this right tail consisting of homes whose selling price extends outward from 100,000 all the way up to 240,000. And so if you go through their little checklist here, you'll see that they come to the same conclusion. Use a density curve to kind of capture the overall shape, and then categorize it in terms of the number of peaks and the skew, and then talk about the shape as right skewed and unimodal. I would make a further point here that prices of homes are economic variables. And it turns out to be the case that in a capitalist economy, economic variables are very often right skewed. And that's because if you think about things like home prices or net worth or annual salary or things like that, very often there's a fixed lower bound for the possible values, right? You can't have a home that's worth less than zero, I don't think. But there's no fixed upper bound in a free economy, right? Some people have homes that are worth 100, 200,000. Some people have homes that are a million, 10 million, or more. And so when that's the case, very often you'll see a right skew in the distribution because there's sort of a lower bound, I guess a lower bound that you can't go below, but then an upper bound that is indeterminate. There's no real upper bound. And so in those cases, you might see right skewed distributions. And economics often has right skewed distributions. Let's see, I wanted to take a look at one other example here. Mary, Mary, quite contrary. Let's see what that's all about. So, Dr. McCoy genetically copied 15 pairs of sunflower seeds. For each pair of identical seeds, so the seeds in each pair are genetically identical, the seeds were planted in separate pots. One pot contained a special blend of fertilizer, while the other pot contained potting soil with no added fertilizer. After 10 weeks, Dr. McCoy recorded the difference in heights in centimeters for each pair of fertilized and unfertilized plants. The results are shown in the stem and leaf plot below. Identify the shape of the difference in height. So we're recording here in this plot the difference between each individual pair of these 15 pairs. Remember, one pair was a seed that was planted in a fertilized plot, and the other pair was a genetically identical seed that was planted in an unfertilized plot. And these are the differences. And so this is a stem and leaf plot, and the differences were fertilized minus unfertilized. So you can see that in a few cases, the unfertilized plant was actually taller than the fertilized plant. You have like minus 1 centimeter for one of the pairs, minus 0.4 and minus 0.3 for the other. But the majority of the pairs, the fertilized pair was taller, and so the differences are positive. This would be 0.2, 0.4, 1.0, and so on. And that's represented by the key here. 1 /4 refers to 1.4. So what can we see from the stem and leaf plot? Well, the stem and leaf plot is really very much like a histogram. You can draw it's like a histogram turned on its side, right? And they're actually trying to show you that here. First, here's a curve that sort of approximates the general shape. And if you rotate that thing counterclockwise, you would see pretty much a histogram for those differences. And you can see from that this is a left skewed unimodal distribution. You've got a few of the differences that were small or actually even negative, where the unfertilized plant was taller than the fertilized plant. But from the majority, the difference was positive. The fertilized plant was between, it looks like, 1 and 3 centimeters taller than the unfertilized plant for the majority of those plots. So a stem and leaf plot is another kind of plot for a distribution. It tells you much the same information as you would get from a dot plot or a histogram, and you can identify the shape of the distribution from a stem and leaf plot by kind of rotating the stem and leaf plot mentally in your head 90 degrees counterclockwise, and there you have the histogram. So these three kinds of plots, histograms for continuous numeric data, dot plots for discrete numeric data, and stem and leaf plots, are all giving us pictures of the distribution of a numerical data. And one of the things we'll be looking at in terms of that distribution is its shape, as we've discussed here. So we'll have some homework problems that take you through a few of these. And as always, if you have questions, get in touch with me via email. In the meantime, y'all take care, and we'll be back at you soon.